Assalamu alaikum. This is lecture 14 on digital control system. We'll be starting chapter 4 today, design of discrete time control system by conventional methods. The methods that we have learned in the classical control, like root locus, frequency domain. So these methods and also stability analysis, error analysis, all these will be discussed in this particular chapter. Since we already have the background knowledge of these articles, now we just have to look how can we relate those ideas in terms of the design in the digital domain. So this is the essence of this chapter. So the first thing we should do is to find the mapping between the S and the Z plane, because we know the conditions of stability, instability, steady state error, all this kind of transient behavior based on the location on the S plane of the poles and the zeros. So similarly, if we can find out similar uh, correspondence with the Z plane, then actually we can also uh, uh, find the relation for the conditions that will dictate whether the system is stable or unstable or marginally stable in the Z plane. So the first step is the mapping between the S and the Z plane. So the S and the Z, the complex variables are related using the formula that we derived earlier, Z equal to e to the power TS. Okay, so S and S is the complex variable in the S plane, whereas Z is the complex variable in the Z plane. Now, how they are as we said that in the from the S plane, what we already know is that in the S plane, the poles in the left half plane actually gives a stable system. Poles in the right half plane gives a unstable system. Poles on the j omega axis gives us a system which is marginally or critically stable. Okay. But in the Z plane, one additional term is introduced, that is the sampling period. Sampling period T. So now, because of different values of the sampling period, it may happen that for the same transfer function, rather pulse transfer function, the parameter may not fall into the zone where it's supposed to be for a stable system. It can go beyond that boundary and fall into the unstable zone. So based on this variable, what is the value you're choosing as a sampling period or sampling frequency, the system may also be unstable. Okay, so same system can have different characteristic based on the sampling period. So that is why it is always wise to specify what is the value of the sampling period at that particular point, because if you change it, system's dynamic is going to change. Okay, so let us start with the formation. First, we know that Z equal to e to the power TS, and also we know that S equal to sigma plus j omega. So if we just straight put it here, so what you are going to get e to the power T sigma plus j omega. And if we extend it, then it is T sigma plus e to the power j and t omega. Now, as you can see, definitely it will be multiplication here. So as you can see, this is nothing but a magnitude. Okay, so basically we can say that this is the magnitude of Z, and this one, from this one we can find that it is actually to the j theta. So basically the angle can be achieved from this one. Okay, so these are the two things. Now, and also as you can see that since the angle is repeated, if you repeat the angle with twice pi. From this one, we know what we know is that cos theta plus j sine theta, isn't it? So e to the power j theta plus twice pi, or any multiple of that, that is k twice pi k plus theta. In that case, we are going to get the same result. So actually, we can say that it will be periodic as well. We can give a k there as well. So plus j sine twice pi plus theta. Okay, so that is why we can also write in this way e to the power t sigma plus, into e to the power j t omega plus twice pi k, which can be repeated with a period of twice pi. So now the poles and the zeros in the S-plane where the frequency differ in a integral multiple of this frequency, which is omega s or twice pi k. So sampling frequency, multiplication of the sampling frequency twice pi by t is mapped into the same location in the Z-plane. So what does it means is, if you have a pole somewhere in the Z plane, and if you have a pole another one with twice pi apart, so they will be plotted in the same location in the Z plane. Okay, so this is S plane. So apart from, again, the gap between them is twice pi, the gap between the next is a twice pi. So all three will be on the same point in the Z plane, say here. So the correspondence is not actually uniform. Correspondence is actually not 1:1. Okay, so what we can say is that from this one, what you can say is that it is actually infinite number is possible. You can, in the negative domain as well, you can find out infinite number of them go up to infinity. So infinite number of values in the S plane is actually have only one value in the Z plane. So this is important to recall. The infinite number of points which are twice pi apart, okay, have same location in Z plane, or the vice versa. One point in the Z plane can have infinite number of points in the S plane. Okay, now from the magnitude perspective, we know that Z, the magnitude of Z is e to the power t sigma. And if the value, we know that from the S plane, that the sigma here is sigma equal to 0 on the j omega axis. And in this location, sigma is negative, and here sigma is positive. Now, first of all, if you want to depict the j omega axis, that means where your sigma value is 0, then the magnitude of Z will be e to the power 0 equal to 1. So the entire Z plane can be actually given with a magnitude of 1 with a variable angle that is different. So what you can say is that the Z plane can be the j omega axis in the S plane can be mapped by a unit circle. So with a magnitude of 1, that will be your j omega axis, equivalent to the j omega axis. So in the Z plane, this is what we have. Okay. And in the left half plane, so in the left half plane, this plane, we know that sigma is negative, and it means that the magnitude Z will be e to the power sigma, and negative sign will be there if you just take the magnitude of the sigma. So which will be actually lesser than 1. Okay. So imaginary axis is a unit circle with magnitude, the magnitude or the radius of which is 1. And also we find that for left half plane, the magnitude have to be lesser than 1. So the left half plane will be mapped inside this circle. And what about the right half plane? The right half plane in the S plane is, we know that sigma is positive. So what does it mean? It will be the magnitude of Z will have to be greater than e to the power t sigma, and which has to be greater than 1. What does it mean? The rest of the location outside in the j omega axis will be actually, that means this location here, this is your right half, equivalent to your right half plane. Okay, so this is your right half plane equivalent. This is your left half plane equivalent. And the j omega axis is your on the surface of the unit cycle. That is your equivalent to your j omega axis. Okay, now the primaries and the complementary strip. So mapping is done, a bit of it. Now, because of the multiplicity of twice pi that we have seen, if they are apart by twice pi, then how we actually have to repeat the thing. So for that, we have to discuss about primary strip and complementary strips. What does it mean? Note that since the angle of z is omega t, we know that e to the power j theta, theta is our angle. So in our case, we have e to the power j t omega. So t omega is the angle. And if we vary the angle of z from minus infinity to infinity, as omega is varied from minus infinity to infinity, then what we are going to see. So for that, we can find out the correspondence. Say that we start with plotting, because one of the parameter that is introduced is the sampling period or sampling frequency. So this is sigma, this is j omega, these are the axes. Now say we have j omega s by 2, sampling by 2, sampling frequency by 2. Here we have angle minus j omega s by 2. So we want to see if we change from minus j omega to omega 2, then how it is linked with our z plane. So angle. So angle wise, how can we find out? Now, as you can see that minus j omega is by 2, and omega t is the angle. So if you replace omega by omega s by 2, and your t is also there, so omega is nothing but twice pi by t. Then you have t as well. So t and t getting cancelled out. So this one is getting cancelled out. So basically what you are going to get here is corresponding angle is basically pi. Okay. Similarly, if you take it minus, oh sorry, we already taken minus, so you just give it minus. So basically we're talking about this one minus pi. Similarly, omega s by 2, since the magnitude is same, it will also be the same procedure, and what you're going to get is pi. So minus pi to pi, this is what we get. So basically minus pi is somewhere here, and pi is also somewhere here. So minus pi to pi, there is a change. And what is your magnitude in this line? In this line, since sigma is 0, so magnitude is 1. So basically what we are going to get is from minus pi with a magnitude 1, we are going to get a unit circle like this. Okay, so my one is not properly drawn circle, but if you want, you can also introduce circle from these shapes as well. So, but it's time consuming. So just assume that even though Y1 is not good, but it is a unit cycle. Is it okay? So from minus pi with a radius of 1, it is eventually going to plus pi. So this is the direction counterclockwise. Okay, so if you move from this direction to this direction, you are having, you can also introduce some intermediate factor if you want to prove that whether it is actually going counterclockwise or not. You can take here minus j omega s by 4, then you will see that it will give you minus pi by 2. Then at the center, you're going to get 0. Then you'll get pi by 2, eventually pi. So it is actually rotating counterclockwise direction. Okay, so it is true for in between these two, and this is what we are calling the primary strip, because we know that if it is repeated, it will give the same unit circle again and again. So if you start from, this is what we call primary strip, because we know that same location in the Z plane will give infinite number of point in the S plane. So this is what is called primary strip. Primary strip. And if you start now from this location, which is pi, then you go up to j 3 pi by 3 omega is by 2. Another omega is gap. Then you are going to get that you are going to get twice pi. So basically, you are going to start from this same location, then another round you go, and eventually you'll go into twice pi. Okay, so same thing will be repeated, and also in the negative one as well. So if you go into the next one, that minus j 3 omega s by 2. So encirclement of the origin with the radius of 1 is being repeated. So other zones, infinite number of them that we are getting as long as you go in the positive infinity on the negative infinity. These zones are, which are identical with the primary one, is called complementary strips. So these strips are, maybe it would have been better if we use another one. So these are called complementary strip. So a pole here and a pole in the same location in the next one, or in this one, they will give the same location in the Z plane, say here. Okay, so this is what is primary strip and the complementary strips. So as long as our sampling theorem is fulfilled, that means highest frequency component is within the twice of your sampling frequency, then actually all the components will be within this boundary. So you don't have to bother too much about it once the sampling frequency is fulfilled. Otherwise, some but some component may go beyond the region of the primary strip. Okay, so now say since we already have drawn the primary strip, how can we correspond the entire primary strip into the Z plane? So say that this is our primary strip within j omega s by 2 to minus j omega s by 2. So this is our primary strip, entire primary strip. Okay, so just consider this one. So let's say we start from this location 1, then we go up to this one 2, then we go 3, then we go 4. Okay, then finally 5, then we go to 1. So we're moving in this direction. So how to represent the strip, the entire primary strip in the Z plane. So we know that we have to draw a unit cycle, a unit circle with radius 1. Okay, now let us see how can we, there is reference, but if you want, you can also avoid that one and then start with, we know one thing is that sigma value is 0 here. And it means that magnitude will be to the power T0, that is 1. And also we know that angle here at location 1 will be 0 as well. So e to the power T omega, omega is 0. So angle is also 0. So you know that magnitude 1, angle 0. So this is your location 1. Now next one is angle, magnitude is remaining 1, but what we are going is from angle is shifting from 0 to pi. We already discussed from 0 to pi. So basically with the magnitude 1, it will be going from 0 to pi. It is not properly drawn, but okay, so with the magnitude 1, so 0 to pi. So now you're here at pi. Okay, so pi somewhere here. Now from pi, now what is increasing? Your sigma value is increasing, and which is negative as well. So negative increase in the sigma is actually making your magnitude e to the minus tau sigma, making it more and more small. So magnitude was 1, gradually at infinity e to the power minus infinity is becoming 0. So what we are doing here, the angle is same, pi, we are in the same location, but magnitude is reaching to 0. Then you have a shift of angle from pi to minus pi with the magnitude 0. So from pi to clockwise direction, you will have pi to minus pi, a shift. Still you are at 0 location, but your angle is now minus pi. So this was your point 1, this is your point 2. Now this is your point 3, and this is your point 4. From 4 to 5, as you can see, the magnitude from 0, it will be gradually becoming 1. The angle is remaining same. So in the same angle, the magnitude will be becoming from, sorry, it should be a straight line. Okay, so something like this. So you're reaching at 5. Okay, so this is where it was pi. Now you have minus pi in this location. Now, as you can see, from 5 to 1, again, magnitude is 1. So you will have a symmetrical pattern, something like this. Okay, so the entire primary strip can be mapped in the Z plane. This is your S plane. And this is your Z plane. Okay, so 1 corresponds to 1, 2 corresponds to 2. This is how you have to map the entire the primary strip. The other strip, it will be identical. So it will be just another trace on the same path, nothing else. Now, the few common things that we have seen in classical control is constant attenuation, constant frequency, constant damping ratio lines. So this is also we want to map here. So the first one is constant attenuation line, constant attenuation line, or they're calling is loci or locus, plural of that, loci. So say that we have in the S plane, we have two constant damping ratio line or constant zeta line. So says this is zeta 2 and this is your zeta 1, which is minus zeta 1. Okay, so this is your origin and your axis, j omega and zeta. Now, how can you represent this one in the z plane? So in the z plane, we know that j omega line is a unit circle. So you can just draw the unit circle in the j omega line. And we know that in any particular constant attenuation line, e to the power sigma is remaining same. So the magnitude will be remaining same as long as your sampling period is same. So it will give another circle line. This will also give another circle line. Now, whether it will be inside the unit circle, so this is your unit circle. So whether it will be inside or outside, it will depend on which side you are. If you're in the left side, your sigma is negative, then it has to be inside because left side is inside the unit cycle. So you will have another one with this one. So, and the radius of this one will be e to the power tau sigma 1. Okay. Similarly, the other one that we have, okay, so now